Has the universe always been the same, or has it changed over time? This question was answered by discoveries made in the last century. In 1929, a significant discovery occurred. The discovery made by the astronomer Edwin Hubble, who observed that our universe is not static but is expanding. What's particularly interesting is that Hubble formulated the law describing this expansion. This discovery is not only fascinating but also one of the most important in the history of science, as it changed our understanding of the universe and led to a new theory, the Big Bang Theory.
That's a fascinating way to visualize the universe. You might envision it as a vast, multi-layered grid or a series of translucent sheets, each representing a different era in cosmic history. Since the universe is expanding, hypothetically, tomorrow the size of our universe will be larger, meaning that the distances between galaxies and stars will be greater. However, if we travel back in time, the universe was smaller in its early epochs. Thus, the distances between galaxies and various objects would have been smaller. In other words, by traveling back in time, the distances between different objects would have decreased. As a result, moving back in time leads us to the moment when everything, every star, every galaxy, every particle, and indeed every object, was located at the same point. This point in time is referred to as a cosmological singularity, which corresponds to the Big Bang, after which the universe began to expand. Of course, this does not mean that it necessarily corresponds to a singular point from which the universe began its existence. Simply put, according to Einstein's general theory of relativity, we cannot describe the universe at distances smaller than those at the cosmological singularity. This idea forms the foundation of the Big Bang Theory. Hubble's discovery proved that the universe is expanding. After that discovery, Albert Einstein no longer had the basis to reject the model of an expanding universe, especially since his equations also predicted such expansion. Here, Hubble's law of expansion is represented. It describes how two objects separated by a distance, d, move away from each other at a speed, v, that is directly proportional to that distance. This relationship is expressed by the formula where h0, Hubble's constant, is named in his honor and has a specific numerical value. The accompanying graph illustrates Hubble's law of expansion, with points representing measured velocities and corresponding distances. Notably, these points align along a straight line, confirming the validity of Hubble's law. In summary, the law of expansion is clearly demonstrated.
It is a curious fact that during Hubble's life, the Nobel Prize in Physics did not cover astronomy. Hubble spent much of the later part of his career attempting to have astronomy considered part of physics, instead of being a separate science. He did this largely so that astronomers, including himself, could be recognized by the Nobel Committee for their contributions to astrophysics. This campaign was unsuccessful in Hubble's lifetime, but shortly after his death, the Nobel Prize Committee decided that astronomical work would be eligible for the Physics Prize.